So we move on to the last section of module 3. So that is stability by using Gleichner's method. So here we look at the condition for analyzing the stability using a method given by Gleichner. So let us start with our autonomous system. So we have the system dx by dt equal to f of xy and dy by dt equal to g of xy. So let us call it as equation 1. And again, for the system, we assume that 0, 0 is an isolated critical point. Now, for this autonomous system, dx by dt equal to f of xy and dy by dt equal to g of y, we will obtain a solution of the form x equal to x of t and y equal to y of t. So this will represent some curve c in the xy in the plane. So let me take c as the path which is given obtained from the equation 1. So c equal to x of t y of t be the path of 1. And let us consider function e of xy such that e of xy is continuous and have continuous partial derivatives in a region which is containing this path. So there will be set of all xy such that that lie on the curve C, and let us take E to be a function such that it is continuous and has continuous first partial derivatives in a region which contains this path. So that is how we choose the function E. Now, since our path C is contained on E of xy, so z equal to E of xy, that will be a surface, and the curve C lies along this particular surface. So for the points which are on the curve C, your given surface will also will satisfy those conditions. അതായത് നമ്മൾ ഈ എന്ന് പറയുന്ന സർഫസിൽ കണ്ടെയ്ൻ ചെയ്യുന്ന പോലെയാണ് നമ്മൾ നമ്മുടെ കർവ് ചൂസ് ചെയ്യുന്ന പാത്ത് ചൂസ് ചെയ്യുന്നത്. സോ therefore E will, so when you substitute x equal to x of t and y equal to y of t, that we will obtain the value for E. So if a point xy moves along the path in accordance with the equation x equal to x of t and y equal to y of t, then in that case E of xy can be regarded as a function of t along C. So along C, E will satisfy x equal to x of t and y equal to y of t. So therefore we can obtain a function of single variable which will be denoted by E of t from E of xy. So E of xy will be equal to E of, so x of t varum, y of t varum. So this will reduce to a function of single variable. Now since it is a function of t, so we can find out what d by dt. So d by dt will be dou e by dou x into, by chain rule, that will be dou e by dou x into dx by dt plus dou e by dou y into dy by dt. Now from our autonomous system, we have the values for dx by dt and dy by dt. So dx by dt is f and dy by dt is g. So d by dt will reduce to f dou e by dou x plus g dou e by dou y. Now let us look at the function E of x. So let us keep this here. So d by dt will be f dou e by dou x plus g dou e by dou y. Now let us define 4 definitions. So the definitions are when is E said to be positive definite, negative definite, positive, semi-definite, and then you have negative semi-definite. Okay. So suppose we are given the function E such that it is continuous and has continuous first order partial derivatives in some region containing the origin. Now if E of 0, 0 is equal to 0, so if E vanishes at the origin, then we say that E is positive definite if E of xy is greater than 0 for all xy not equal to 0, 0. So if E of xy vanishes at the origin, and then E becomes positive definite, E must be greater than 0 for all points other than the origin. And similarly, E is negative definite if E vanishes at the origin and E of xy must be less than 0 for all xy not equal to 0, 0. So if you look at say this equation z equal to x square plus y square. So this is an equation of a paraboloid. So look at three-dimensional space the paraboloid എടുക്കുമ്പോൾ, so you can see that so it is centered at the origin, so it vanishes at the origin, but for all for any other point xy not equal to 0, 0, we can see that E of xy is strictly greater than 0. Now same way, if we take z equal to minus of x square plus y square, so you will get a paraboloid opening downwards. So again that will be negative. E is positive semi-definite if E vanishes at the origin, and E of xy greater than or equal to 0 for xy not equal to 0, 0. Now the difference between positive definite and positive semi-definite is positive definite in origin മാത്രം ആവശ്യമുണ്ട്, ബാക്കിയെല്ലാ പോയിന്റിലും be greater than 0 ആയിരിക്കും. So for positive semi-definite can vanish at xy not equal to 0, 0 also, but the value of E will be greater than or equal to 0. And again same for negative semi-definite also. So if E vanishes at the origin and E of xy less than or equal to 0 for all xy not equal to 0, 0, then we say that E is negative semi-definite. So it vanishes at the origin. We can also vanish at other xy values also other than the origin. So that are the definition of E to be positive definite, negative definite, and positive semi-definite and negative semi-definite. So common example or a general example of positive and negative definite function is, so if you take functions of the form a x raised to 2m plus b y raised to 2n, where a and b are constants and m and n are positive integers. So as you can see, this is even powers. So at 0, 0 it will be vanishing. Now when x or y is not equal to 0, this will be greater than or equal to 0. Since you have even powers, x raised to 2m, y raised to 2m. So when x is greater than 0, y is greater than 0, I will usually at terms of positive variable. Now if I am taking a and b to be positive constants and m and n to be positive integers, so you can see that the sum will be always greater than 0, and at xy equal to 0, 0 it will vanish. So that is an example of a positive definite function. And similarly, if you take a and b to be negative and m and n to be positive integers, so we will be getting a negative definite function. Or if E is positive definite, then minus E would be negative definite. So that is said here. So E of x is negative definite if and only minus E is positive definite. So functions of the form a x raised to 2n plus b y raised to 2n with a less than 0 and b less than 0 are negative definite. But നമ്മൾ individually ഈ functions നോക്കിക്കഴിഞ്ഞാൽ അത് positive definite ആയിരിക്കില്ല, positive semi definite ആയിരിക്കും. So if you are looking these functions alone, x raised to 2n ആ combination വരുമ്പോഴാണ് നമുക്ക് positive definite negative definite വരിക. Now provided both coefficients are positive or negative. So if you look at this function x raised to 2m, you can see that it vanishes at the origin, but it can be 0 at other points also. It's always greater than or equal to 0. If you 0, 1 എന്ന് പറയുന്ന point എടുത്തു കഴിഞ്ഞാൽ 0, 1 ന് x raised to 2m ന്റെ value 0 ആണ്. So you can find a non-zero point where this vanishes. Same holds for y raised to 2n. അതുപോലെ x minus y whole raised to 2x. So you're taking a point 1, 1. Okay. So if you are taking any point such that x equal to y, this will vanish. So we get that it vanishes at a point other than the origin. But again, it is always greater than or equal to 0. So hence, these functions are positive semi-definite. Now, നമ്മൾ ഈ കോൺസെപ്റ്റ് ഡെഫിനറ്റ്ലി കോൺസെപ്റ്റ് നമ്മൾ നോക്കിയത് ഇപ്പോൾ. So from this we are going to now define Lyapunov function, and using Lyapunov function we will look at the stability of the autonomous. So let us now define a Lyapunov function. So a positive definite function e of xy with the property that so we have seen this term dou e by dou x into x plus dou e by dou y g for the autonomous system. So if e is a positive definite function and if the function dou e by dou x into f plus dou e by dou y into g is negative semi-definite, then such a function is called a Lyapunov function for the system. So you are given an autonomous system of the form dx by dt equal to f and dy by dt equal to g. Now e is a function for which we define that it satisfies certain conditions. Okay, there can be different values for e. So find a function e such that it is positive definite and dou e by dou x into f plus dou e by dou y into g is negative semi-definite. So such a function is called a Lyapunov function for the autonomous system. Now let us look at a theorem on stability using the Lyapunov function. So if there exists a Lyapunov function e of xy for the system 1, so that is our autonomous system, then the critical point is stable. So provided you can find a Lyapunov function e, അതായത് e positive definitive ആയിരിക്കണം, dou e by dou x f plus dou e by dou y g negative semi-definitive ആയിരിക്കണം. So if such a function exists for the autonomous system dx by dt equal to f, dy by dt equal to g, then the critical point will be stable in that case. And again, if this function has the additional property that the function is negative definite. So instead of negative semi-definite, if it turns out to be negative definite, dou e by dou x into f plus dou e by dou x into g negative definite ആണെങ്കിൽ, in that case the critical point will be asymptotically stable. So that is the Lyapunov's condition for stability. For if you can find a Lyapunov function e such that Lyapunov function e, then it is stable, and Lyapunov function negative definite ആണെങ്കിൽ it will be asymptotically stable. Let us look at an example to analyze the stability using the Lyapunov condition. So we are given the second order equation. So let me take dx by dt equal to y. So we will get m. This will be dy by dt, that will be equal to minus c. So dx by dt will become y minus kx. So therefore dy by dt will be equal to minus c by my minus k by m x. Now let us define, let us take e to be the function. So let me take e of xy to be m by 2x y square plus k x square by 2. So here as we know, m is a mass, so m will be greater than 0 and k is going to be greater than 0. So therefore e of xy is greater than 0 for xy not equal to 0, 0, and when you take e at 0, 0, that is equal to 0. So therefore e is, as you can see, e will be positive definite in this case. So dou e by dou x into f plus dou e by dou y into g, so that will give us minus cy square, which is less than or equal to 0.